Welcome to Transfer Phenomena in Bioprocess Engineering Week 2 session. Aspect of rheology in Bioprocess Engineering. So, here the viscoelasticity of non-Newtonian fluids. So, what do you mean viscoelastic? So, viscoelastic we can differentiate two types. So, one is the viscous behavior. So, other one is for elastic behavior. For viscous behavior, the energy dissipation during the flow, but the elastic energy storage or energy recovery the flow. So, both are the difference here, that is the viscoelastic. So, what are the mechanical response depends on here. The first is the magnitude of applied stress, how much stress we applied here, that magnitude is the first point. Then the duration of deformation. So, how much the deformation duration, then what is the history of applied shear. So, these are mainly depend on here. So, what are the fundamental, the physical concept of this one? Of course, already we last class we discussed what is Newtonian. So, always the n stands 1, we always call as a Newtonian flow. If it is very purely viscous, it is a Newtonian fluid. But again the stress is the proportional to the rate of deformation, if it viscous. In the same case, if it elastic there, then the stress is the proportional to deformation. The first one is for the stress, the proportional to rate of deformation, The second one for here the for elastic solids, the same stress is proportional to only for deformation. So, what is the viscoelastic fluid combines both responses here. The stress is again here, the stress is the function of, there is a strain, we are discussing the strain, then the strain rate, what is the deformation, the rate of deformation, then of course the time also factor here. So, the viscoelasticity, the stress is function of strain, then the strain rate, then time. So, what are the effects of elastics under shear? When you apply shear, what will happen? When you release the shear, what is happening? So, during shear flow, so there is a elastic energy during the flow, elastic energy stored in the molecular conformation. But same way for polymer chains or macromolecules, the stretch and orientation here. But when you remove the shear, the first one is for the during shear flow, the second is when shear is removed, then it stored elastic energy, whatever the elastic energy stored here, that may be released. Then the fluid may be recoil or the flow should be a reversal. So, when during flow is different, if you remove the shear, that is a different here. So, what happened here, the key here, the direction of flow, it may reverse if you stop the shear. The shear, if you stop it, the direction of flow suddenly change that one. So, what is viscoelastic fluids here? Of course, this already we discussed the relationship with the other non-Newtonian behaviors here. The most viscoelastic fluids are, one is for shear thinning, that is called shear thinning. We always already discussed the same thing, shear thinning. Then that is called the pseudoplastics. Then possibly thixotrophic also there. Sometime the yield stress, the tau naught, we always discuss a tau naught, yield stress is there. So, hence viscoelasticity is rarely in the isolation part here. So, the viscoelastic fluids in bioprocess engineering, since we are discussing the bioprocess engineering, so we have to focus what is the common bioprocess examples in the viscoelastic fluid in the bioprocess engineering. So, we already discussed the polymer solution, xanthan gum, alginate, then PG. These are the best example for here, bioprocess example. So already we discussed same thing, fermentation broth rich in the extracellular polysaccharides. Then the fungal mycelial culture with the filament, same for cell polymer suspensions in the biomedical wherever use the bioprocess. So these are the common bioprocess example for viscoelastic fluid here. So why viscoelasticity is a matter in the transport phenomena? Because if you want to discuss about the movement and transport, because the first classes we discuss what is the movement and transport, then mass transport, then heat transport. So the movement and transfer is only the function of, there is a velocity is the driving force. Whenever if you discuss the heat transfer, the heat transport, then the temperature is the function of temperature, that's a driving force. And then if you talk about the mass, then this is a function of concentration. Concentration is the driving force. So the movement and transport is influenced by normally the elastic normal stress, then shear rate dependent viscosity. Okay, if you assume classical Newtonian fluid, what will happen here? But there is the real flow, but if you assume as a Newtonian fluid, then definitely it's a fail to predict the real flow, because already it behaves as a non-Newtonian, but you are assuming as a Newtonian fluid, and then definitely they predict the real flow pattern. So why you want to this one for accurate modeling is essential for scale up. When you want to scale up, always we discuss the batch to, okay, batch to scale up that one, then of course we need a accurate modeling what exactly happening here. Then second point is the reactor design. What is this one? The third is for CFD simulation for bioprocess equipment. What is CFD here? Computational fluid dynamics. That's a different this one. For that simulation of bioprocess equipment also is very accurate for the modeling here. Okay, so accurate viscosity measurements, why you want to do here? The essential here. So of course, it's essential for when you characterize the fluid flow, whether it's a laminar flow or turbulent flow or transition flow, what type of flow. So definitely we need the characterizing fluid flow behavior, and when you want to design and the scaling the bioprocess equipment, we need that accurate viscosity measurement. And of course, you want to predict the movement and transfer rate or mass transfer rate or flux, whatever here, that viscosity is a main role for accuracy here. So for wide variety of viscometer, of course, what is viscometer for available for the rheological characterization? You want to measure rheological characterization, of course, we have to use the viscometer. So what are the viscometer here? The primary objective is to establish a controlled and well-defined flow field here. So what you want to measure the physical quantities here? One is a shear stress, then shear rate. We already discussed the Newtonian tau equal to mu of dV by dy, okay, then n. So this is shear stress, the tau, then the shear rate is the dV by dy. Already we discussed, and what is the units. So the both the parameters very important for this one. So you want to enable here, if you want determination of viscosity in the Newtonian fluids, that is very important. So if it non-Newtonian, of course you want the rheological parameters also estimate. So what is the principle of operation of viscometer? So most viscometer operating by imposing the rotational motion on the test fluid. Whatever you want to measure the fluid, the rotational motion is here, very important. So two fundamental quantities are measured. What are the quantities here? One is the torque we always write M. M is a torque. Then other one is for angular velocity omega. So the rate of deformation imposed here, this angular velocity then M, you have to measure both here, the torque. These quantities are converted in terms into, one is a shear stress, then we always write the shear rate. But not only this one, but we have to use for the geometry dependent relationship, then what is the calibration constants the specific to the instrument. These are both are first you measure as this one and the torque, then angular velocity, then you convert as a shear stress, then shear rate. So, here from measured quantities to rheological parameters, same thing what we discussed, one is the torque, then another one is for angular velocity. So, the shear stress, first shear stress, the tau equal to function of torque, then geometry, whatever geometry that you have to use here. Okay. Same way for shear rate, the shear rate, we write shear rate is a function of angular velocity, then geometry. So, where we have to use the evaluation here, the viscosity for a Newtonian fluids, that is first one, then consistency index, we always write K. We last class we discussed how the K responds with the concentration, with respect to time, all we discussed the previous class. Then how the flow behavior index N is a dimensionless, that also the, then yield stress for only for non-Newtonian fluids, that is a tau naught for non-Newtonian fluids. Then we will discuss the what is the modern rheometers. Of course, we have to measure the viscometer here. So, most of the latest all the microprocess control. So, we can measure directly, direct readout of the shear stress, directly we can measure shear stress, then shear rate, then apparent viscosity. So, then the capable of steady shear test, that also we can do. Then time dependent, we always write a thixotropic measurements, then oscillatory rheology. So, if you want viscoelastic characterization, that also possible. So, what are the three type of the basic viscometer in the bioprocess application? The first one is for cone and plate viscometer, the second one is for coaxial cylinder viscometer, the third one is for impeller viscometer. We will explain one by one, discuss here. So, the cone and the plate viscometer, what is the principle and configuration here? It's anyway is a float, this is called a stationary plate, already there, stationary plate, and this is a rotating cone, here rotating cone. Then the test here, there is a narrow gap between the cone and the plate, there is a cone and the plate, there is a gap is here. The cone angle here, the theta here is always the less than 3 degree, the cone angle is here less than 3 degree. If you make a small angle, if it's small angle, you ensure the uniform shear rate throughout the process. It's also simplified and give the accurate rheological analysis. But when you make a large cone angle, if you increase the 3 degree, then what will happen? Then shear rate, whatever shear rate, that become as a non-uniform. Then analysis of non-Newtonian fluids is a more complex, and of course, it's a very impractical. So, the angle, the cone angle here, theta 3 degree, if it's deviate, it's always deviate from the ideal flow assumptions. So, what is the operating principle here? So, one is the angular velocity, then other one is a torque. You can see here, this is a M, okay, that's a torque M, then M here, then angular velocity. So, anyway, the rotating here, that's a measurable quantity here. One is what we are going to measure, angular velocity first, then the torque. So, the angular velocity, these are related to shear stress, then shear rate through known geometric relationship. So, when you want to solve here, when you want to do this one, there is the assumption here. What is the flow assumption here? So, one is a steady state, because with respect to independent of time. But whenever for unsteady state, this is always the function of time. We already discussed the last class also. What is this one? Then it should be a laminar. It's not like a turbulent or some other this one. So, the point is that it's a concentric circular streamlines around the cone axis. So, what is the next steps assumption is the velocity varies linearly, it should varies linearly velocity the gap, whatever the gap is giving, that one. For sufficiently small angular velocity, I mean cone angle, so errors due to deviation from ideal, what we fix this one, it should be this one. For ideal flow also negligible. So, these are the assumptions here. It starts with the steady, then laminar, then it is a concentric circular streamlines. So, then what is the temperature we have to control? The temperature control, you just use the circulating water from constant temperature bath, the below the plate, the first one. But still, if you want effective temperature control, you can always the rotational speeds you can moderate. Through moderate, then we can effective temperature control, we can do it here. The first one is for we discuss the cone and plate viscometer. The second is for coaxial cylinder viscometer, QUIT. The widely used rotational rheometer, you just here, this is a diagram here, and you can see here that is a M, okay. One is a torque, then other one is the angular velocity. Then it is a particularly suitable for moderate to high viscosity. So, moderate viscosity to high viscosity fluids we can use it. Of course, we can use for homogeneous, sometime we can use for heterogeneous, it should be a very light heterogeneous. And the based on controlled shear flow between two concentric cylinder, it is a two cylinders. What is this one? The inner cylinder we always write Ri, the inner cylinder we are writing here, this inner cylinder Ri, then the outer cylinder here R0. So, one is R0, that is the outer cylinder, this outer cylinder, the inner cylinder is a Ri. So, what is the annual gap here? That is a Ri or R0, there is an annual gap here. So, then the height of the liquid height we assume as a h up to this, up to this height is a h. So, what are the mode of operation? There is a two way, either the first one is for inner cylinder is this is rotating, inner cylinder is rotating, but outer is a fixed, or outer cylinder is rotating, but outer cylinder is here rotating, then inner cylinder is a fixed. So, there is a two way to the possible operating condition here. So, one is the angular velocity, that is important here. So, what are the operating principle here? One is the steady state, what we discussed same way, then it should be a laminar circular flow in the annual, not like turbulent or other things. So, the measured quantity here, one is angular velocity, other one is for torque to maintain the rotation. So, from these quantities we can always get the value of shear stress, then shear rate. So, you have to measure the angular velocity, then torque, from there we can get the shear stress and shear rate. So, what is the operating principle here? So, this is a angular velocity rotating with the angular velocity, then other one is for the fluid resistor motion, the generating measurable, that is called torque M. So, once you done for angular velocity, then torque, then we can always get the value of shear stress and shear rate from that one through known geometric relationship. Of course, the flow assumption whatever discussed same way, steady and laminar, and it should be a concentric circular streamlines. The velocities varies the gap, whatever the gap, velocity varies linearly with the gap, that one. Of course, for sufficiently small cone angle, the error due to deviation from the ideal flow are negligible. So, now impeller viscometer, first we discussed the cone plate viscometer, then what is the coaxial cylinder viscometer. This is a impeller viscometer, that is a normally. Here the modified rotational, the rheometric, specifically we use for the complex bioprocess fluids. So, what are the limitation for cone and plate viscometer, then coaxial cylinder viscometer. Particularly this we can use for the fermentation broth with the cell, then mycelia and polymers. Even you can use biopolymers. So, of course, the conventional viscometer, the face challenges when applied to, if it is heterogeneous, it's a very difficult to use, because the assumptions first we discussed, either homogeneous or lightly heterogeneous. But if it heterogeneous fluids, it's very difficult to use a conventional viscometer. If it is highly viscous or shear sensitive broth, we cannot use this one. So, only we have to go for impeller viscometer. So, then system sometimes containing the suspended biomass, they are also very difficult to use. The fermentation, of course, the fermentation fluids also we cannot use here. Whenever the non-Newtonian behavior is very difficult to use for conventional viscometer. If it time dependent viscosity, if it's structural breakdown, whenever if you apply shear, the structural breakdown is also there. So, for this we cannot use for conventional viscometer. So, we have to use for impeller viscometer, because it simulate actually by actual bioreactor hydrodynamics. So, that is the impeller viscometer is the best to use for all the bioprocess, this one. So, what is the basic configuration, the principle here? Instead of replace the rotating inner cylinder with the small impeller, is mounted with the steering shaft. So, the impeller rotates slowly the sample. Again same way we measure torque on the impeller, the shaft, then there is a rotational speeds. Instead of shear rate, we measure here the rotational speed here, that is called Ni, that is a rotational speed. We always write this is a rotational speed. So, from this we can measure the shear stress, then shear rate. So, what is the shear rate estimation here? The shear rate, that is the shear rate equal to K into Ni, that is the empirical here. The K we called as a geometric constant, it is a dependent definite used for impeller. What type of impeller you are using here, based on that it will change. So, example, if you use a turbine impeller, the K value is 10, but if you change the other impeller, the K value vary. There is impeller size is there, then the tank configuration also there. Then the shear stress, we can get a torque relationship from turbine impeller. So, under laminar flow condition, the tau equal to, this is the equation, 2 pi mk by 64 di3, okay, cube. So, the m is here, the m stands measured torque, then the di is the impeller diameter. So, here this empirically only we can use for turbine impellers, this equation. So, the turbine per K values we assume a this one 10, then m value of course we can get it from here, then di of course we can get it also, that is the rotational speed. So, from there we can get a tau value. So, then the exact value of K must be determined experimentally using the standard fluid with the known rheology. Of course, then the calibration ensures that accurate conversion of torque, then speed into the rheological parameters. So, we need critical step before studying unknown the fermentation broth. This is all we need here. So, there is a constraint laminar flow, already we discussed what is laminar flow, NR equal to dV rho by mu, but here is vary. So, the laminar flow, we always write the general laminar flow here. The equation for shear stress valid only under laminar flow, but the laminar flow this one less than 10 only, it is only valid. Then here the impeller Reynolds number or Reynolds number we can write proportional to Ni. So, definitely this restricts for maximum impeller speed, then accessible for shear rate range. So, what are the extension using alternative impellers? We can use some other impellers. So, whether anchor or helical impellers we can use. when you use here, we get a laminar flow higher Reynolds number. Higher Reynolds number, there is the limit is there, but with the laminar flow at higher Reynolds number, of course, we can work for large shear rate range also. So, the advantage is then higher K values. So, better simulation of bioreactor mixing we can use here if we instead of some other impeller if we use. So, what are the bioprocess engineering relevance here? Most reliable the techniques are, one is the mycelial fermentation broth, then highly structured microbial cultures. So, what are the eliminates the common issue in the standard viscometer? First wall slip, then phase separation, then cell sedimentation. So, it directly gives hydrodynamic environment for stirred bioreactors. So, what are the problem associated with the cone and plate coaxial cylinder viscometer if we use here? So, one is the centrifugation induced phase separation, because the rotational motion is always generate the radial centrifugal forces. So, then suspended cells migrate away from the rotating, wherever the rotating surface, it is away from the surface, but definitely the results for lower local cell concentration near the shearing region, underestimating the viscosity. So, the error always large as a 1 or 2 order of magnitude have been reported, already reported that one. The second point, the sedimentation during measurement. So, if inadequate mixing, if it leads to gradual settling of cells or aggregates here, definitely it produces a non-uniform solid the distribution here, and then time varying rheological measurement also need this one. So, these are the problem associated when cone and plate coaxial cylinder viscometer if you use a bioprocess. Then the geometric interference of the cell aggregates here, the typical viscometers are if it is a comparable size, then fungal fillets here. So, then physical blockage is there, sometimes poor repeatability also there. Same way for orientation dependent measurements, then it is a non-spherical cells, then mycelial networks here, it is aligned differently under shear, it is aligned differently under shear. So, the measured viscosity becomes a sensitive to flow history, the history, flow history. So, then measurement duration here. So, we cannot get the non-reproducible rheograms, it gets a different rheogram when you do use the cone and plate and coaxial cylinder viscometer. So, shear induced structural changes, what are this here? What is the aggregation, other one is a breakup aggregates. So, definitely it alters the particle size, then suspension in the microstructures. So, whatever the cell damage, the last one is the viability loss. If it high shear stress high, then definitely this disturb the cell membranes, sometimes break the mycelial filaments. It leads to change in the broth rheology and sometimes the loss of the biological relevance also. So, it is very critical for especially mammalian then filamentous cultures. So, what are the advantage of impeller method for fermentation broth? It's we can use continuous stirring, it prevents the sedimentation, whatever this there is a disadvantage, it is a advantage of here, it is a prevent the sedimentation, it maintain the uniform solid distribution. The flow field closely resembles here the actual bioreactor hydrodynamics, it always minimize time dependent, same way for phase separation here. Why impeller viscometer are preferred for the bioprocessing? Because it is a very suitable for microbial suspensions, then mycelial fermentation broths here. So, it provides the practically relevant rheological data, then better reproducibility than the standard, whatever the standard viscometer, it give more reproducibility. So, widely accepted for the empirical nature of analysis, this one, that is if you use impeller viscometer in the bioprocessing. Thank you. you.